Training Leetcode solution. I wish everyone had a great Thanksgiving and a long weekend so that you can relax. If you want the best marketing interview experience in North America, feel free to check us out at baozitraining.org. We have a single round interview. We also have the 3 rounds interviews with resume revisions. Alrighty, so today we're going to talk about a very classic problem called clone graph. So the problem is, given a reference of node in a connected undirected graph, noted that graph has directed and also undirected. So if you use the edge, the node edge type of way, so directed is one way and undirected is basically both ways. Return a deep copy of the graph. This means if you have a reference neighbor, you cannot just point the pointers. You have to actually copy the entire node, essentially make a new node. Each node in the graph contains a value and the list of node of its neighbors. So yeah, for example, if you have a graph look like this, 1, 2, 3, 4. So 1, this is a node, the value is 1, and then it contains a list of nodes, which is neighbor, which is 2 and 4. The order doesn't really matter because you when you compare two lists, you can always cast them to a set and then compare the value of the two set. And then in this case, 2 has 2 neighbors, 1 and 3. So that means because it's undirected simple graph, that means 1 has a neighbor of 2, 2 definitely has a neighbor of 1. There's a few assumptions. One is the nodes of numbers, so it's a small graph. And it's a undirected graph, it's a simple graph, which means no repeated edges and no self loops. So that means if 1 and 2, they are connected, it has only one edge. It won't have like multiple edges. And also if if there's no loop, means there's not going to be like 1 connect to itself, like this. It won't be something like this, no. And then it won't have 2 edges, no. Back to the problem. So the problem is given that, and then you have an interface, so it's given you a graph is the starting point of the node. Node doesn't need to be a topological graph, which means it doesn't need to have a node that has 0 input degrees and then return the cloned node. So the thought process, I would say, is relatively straightforward. Whenever you're trying to copy something, you're essentially doing a traversal of the entire graph, or else there's no way you can copy the whole thing. There's 3 ways you can do this. One way is using BFS. Actually, there's mostly 2 ways, BFS and DFS. BFS, normally you are utilizing a queue, so that you can maintain the FIFO order, first in, first out. DFS, normally you are using recursion, and also for most of the cases for DFS, you can always utilize the stack to mimic the recursion, essentially using the stack to mimic the functional recursion. And also here, the trick is using a map to keep a one-to-one mapping between the old nodes and also the copied nodes. Meanwhile, we can also use a map to avoid a cycle when performing either BFS or DFS. So let's get right into it. So the BFS way, so here I named the method clone graph BFS. So first you do some null check, you have the map, you always have a queue to maintain the FIFO order. So whenever you add the node into the queue, you want to make a copy of the node so that the lookup, this is the original node, and then this is the copied node. So now the problem is we are doing this template thing whenever they have a node. So we'll basically pull the node and then we are trying to copy all the neighbors. The trick is if the node if the lookup table doesn't have a node, which means it's the first time you're seeing this neighbor, you're gonna make a copy. So note here, the neighbors of the copied node is empty. So that's totally fine because you're gonna put this neighbor into the queue. See here, queue.add this neighbor, because when it gets popped out, now is the time to populate the neighbors of that node. So don't worry about the neighbors of this node. Currently, you can just create an empty like neighbors for this current node, which means this is the first time you see it, and then you put it in the queue. And then you add it later, so that later, when that is popped out, essentially, you will get all the neighbors, even though the neighbors, sometimes the neighbors could be copied or it could be original neighbor, so follow the same pattern. And then after you created this node, the current, so get current, which means get the corresponding copied node of the current and then get the neighbors and then add the copied node here. So if I showing the original graph here, it will look like something. So this is the original node. So first of the queue, so this is the queue. We get the 1 here and then we pop it out 1. And then let's see what is the neighbors of 1, right? why it's drawing two lines. Oops, I think I'm... Okay, so I have the queue. I got the 1 here. I pop up the 1 out, and then I have 2 and 4. So essentially what I'm doing is I'm creating a node 2 and 4 here, and also I populate up the 2 and 4. And then what I'm adding is for the 2 and 4, I'm adding the neighbors 2 and 4 at the same time. So now, for example, when I pop the 2 out, so what is the neighbor of 2? So you have 1 and you have 3. So because the lookup table already contains 1, so 1 is already here. And then the 3, so there's no 3. So essentially you have to create a new node of 3, and then you're going to put it into the queue. So your lookup table also serves as a kind of like a dedupe type of thing, right? So if it already has the node, so here, look at here, so you directly copy, you won't put it into the queue again, so that you won't have an infinite loop. So time complexity is O(n) because you have to visit each node once. Space complexity is O(n) because you need an extra queue and also an extra map. And okay, so let's see the DFS using recursion. So I did not paste the code here. So the using the recursion is essentially a similar idea. So let's see. So this is DFS using recursion. So all we have here is, so first, normally whenever we do recursion, we need to have a helper function. So the helper function is also you're gonna pass in kind of like a memory lookup type of, not memory lookup, like more like a lookup thing, lookup table, so that you will not having like an infinite loop by repeatedly looking after node over and over again. So the lookup is the same. This is one-to-one mapping. So this is a kind of like a post-order traversal, which means you are doing lots of things. You're copying all these neighbors. So once you have a node, right? You copied all the neighbors, and then you return the copied node back, and then you link it to the neighbors. So essentially what we do is, so we will check, have you ever seen this node? If you see this node, we'll return the copied node, right? And then if you haven't seen this node, what we do is we create a new node. We put this node into the map so that we remember we've seen this node. And then now we need to copy the neighbors. So we're going to recursively copy its neighbors. Whenever we see a node, we're just going to recursively call this. And then after this node is copied, and then this copied node neighbors will add, this copied node will add its copied neighbors. Yeah, it's basically a DFS method. So the space and the time complexity is also O(n) because you visit each node once. Same thing, you're going to use a extra map, even though here I'm not counting the recursion function stack. So for any kind of recursion, like I said, you can use a stack to achieve the similar thing. So the code structure looks exactly like using the queue. The only difference is instead of using a queue here, you're going to create a, oh, I think I messed up. This is actually this is using the recursion, so the stack one. So it's okay. Let me see here. This is the using stack one. So using the stack, code structure is similar as a queue. So all the differences here, you create a stack, and then instead of pushing to the queue, now you push into the stack. Why is it like a recursion? Because here, whenever you push the queue, you always pop like 2 and then 4, 3. So for using the stack, the difference is, so now if you for 1 you push 1 out, and then you have the neighbors 2 and 4, right? So whenever you pop, you're going to pop up the 4. So whenever you pop up 4, you will have 1 you already cloned, and then you will have 3 that you haven't cloned, and you will push back 3, and then you will pop up 3. So 2 will be handled the last. So other than that, it's a similar thing, and then it's going to be the similar time complexity and time and space complexity as using a queue. The last part I want to mention is if you're actually doing an interview, right? So once you finish the code, how can we ensure actually the node is cloned? So normally what I would do is I would just basically, just manually create a graph. Doesn't need to be fancy. Like for example, this is exactly the N1 to N2 that I will create a graph like this. And then how do you know whether this 2 is correct? So you're gonna print it out in certain orders. I'll just print it out into a BFS order. For example, given any node 1, right? So I'll print it out into like 2, 4 because it's a BFS way, and then we'll print out like 3. So it's not a topological order because this is essentially a graph. There's no topological order essentially. So, but the point is, given this BFS way, whether it's printed a 1, 2, 4, 3 or 1, 4, 2, 3, both of your graphs needs to print out the same thing. So once you have this, and you can have a main method to test both of the method to compare the orders, they're actually the same orders. So when you printed the graphs. And also note here, right? So even though it says it's not it's a simple graph, so even you have this case, you have a circle, it also works fine, because once you have a circle, it's you create this node, you put it in the map, and everything is already working, because once you check the node, oh, you already created this node, they're gonna link it itself. So you can actually try it out. If you create a node and like this will also work. Just saying. So you can also point it out to your interviewer. That's pretty much about it. So I also linked the official Leetcode solution, which is essentially like what I said here, and also the Code Ganker CSDN here. So I really like this guy, Code Ganker. It's kind of like playing Dosa. Anyways, I will fix the blog, and happy Thanksgiving again, and best of luck. See you guys next time. Ciao.